Check it out now, y'all.
NanoHub U, online instruction.
Okay, welcome back. This is the second lecture on probabilities, and what we're going to do in this lecture is we're going to discuss three examples to try to provide some specific examples, specific problems that are related to the concepts that we discussed in the previous lecture. So the first example we're going to deal with is a pretty simple example. It's like to set it up. It's like we've got a box. Inside this box, we've got a large number of red and blue marbles. There's actually equal numbers of red and blue, and there's very many marbles. And so what you do is you put your hand in this box and you pull out a marble. Well, the probability of pulling out a red marble, because there's equal numbers, right? The probability of pulling out a red marble is 1/2. The probability of not pulling out a red marble, that means pulling out a blue marble, is also equal to 1/2. And so then it's possible to enumerate, if you, let's say, decide you're going to do an experiment where you pull 4 marbles out of the hat, right? You can enumerate all possible outcomes of those four marble pools, right? So one possible outcome is 4 reds, another possible outcome is 4 blues, yet another possible outcome is 2 blues and 2 reds. You can, for these middle outcomes, right? 1 red, 3 blue, 2 blue, 2 red, 1 blue, 3 red. There are different ways those marbles can be pulled out. Those different ways lead to different multiplicities. And so I've tried to just schematically indicate the different ways you can get, let's say, 1 blue marble when you pull 4 marbles from the hat. Right, so the multiplicity of this particular outcome is 4. The multiplicity of the 2 blue, 2 red outcome is 6. And you can add up all these multiplicities and it gives you a total number of 16 possible outcomes for this extremely simple experiment. Now, once you know, the key point is once you know these different outcomes, then you can start to answer all kinds of interesting questions. So for instance, what's the probability that you're going to pull out, let's say, 2 blues and 2 reds, right? Well, there are 6 different sequences of 2 blue and 2 red. That's the multiplicity 6 that we wrote down here on this slide. So there's 6 different ways that outcome can occur. There's 16 total possible outcomes. So the probability of pulling 2 red and 2 blue is just the ratio of 6/16, which is 37.5%. So clearly, if you're a betting person, 37.5% of the time you're going to pull 2 blue and 2 red. So that's the outcome that you would likely put your money on, because that's the outcome that's most likely to occur. So these probabilities, right, that you get from this very simple argument, they have a very discrete range. They go from 0 to 1. So the probability of unity means that with 100% certainty, you're always going to get the same outcome. With a probability of 0, that means you're never going to get the outcome that you want. And all probabilities lie in that range between 0 and 1. The other point that I guess should seem obvious is that the sum of the probabilities for all the events must sum up to unity. So for instance, if I calculated the probability of each of these 5 outcomes, and if I added those probabilities up, I'm going to have to get unity by definition. So that's another feature that's useful to appreciate. How do you predict these multiplicities or weights or these degeneracies? Right? If you have to draw pictures like this, it quickly becomes intractable, because this is the case for, let's say, pulling 4 marbles out of the hat. What happens if I pull 10 marbles out of the hat? How would I predict the multiplicities for each of these different outcomes when I start to increase the number of marbles in a particular experiment? Well, The answer to that question is that the weights or the multiplicities can be generated mathematically. They follow from these binomial coefficients, and these coefficients are defined such that the number in a subsequent row is just given by the sum of the two numbers directly above it. And the outermost edges of each possible set of outcomes is always 1. So for instance, you can see that the case we just discussed was n equals 4. This was the case of pulling 4 marbles out of the hat. The multiplicities are 1, 4, 6, 4, 1, and they're generated by propagating these numbers downward. This chart is very easy to remember, so it's simple to write down when you need to use it. But it's useful to also have a more general formula. And the more general formula I've got written down here, this is the multiplicity for pulling n red marbles and n blue marbles out of the hat. So n sub A is the number of red marbles you pull out, n sub B is the number of blue marbles you pull out, n is the total number of marbles that you're pulling out. So for instance, just to illustrate this, let's pick the case n equals 6. n equals 6 means we're pulling 6 marbles out of the hat. We want to know what are the number of ways that you can pull, let's say, 6 red marbles out of the hat. Well, the number of ways you can pull 6 red marbles out of the hat is 1. There's only one way to do that. There's only one way to pull 6 blue marbles out of the hat. So that defines the two endpoints in this sequence. You can ask what's the probability of pulling 3 blue and 3 red. That number turns out to be 20, and that's evaluated by putting the number of red marbles equal to 3, the number of blue marbles equal to 3, and then calculating 6 factorial over 3 factorial times 3 factorial. And if you evaluate that, you'll find out there's 20 different possibilities for that event to occur. Another standard example is the standard deck of playing cards, right? I can ask, what is the probability of pulling an ace of hearts out of this deck? So if I shuffle the deck, right, and then I just take the top card, right, probability of pulling an ace of hearts out is going to be 1 in 52 because there are 52 cards in this deck. And there's only one ace of hearts, right? So if the deck is randomly shuffled, right, the top card should always have a probability of 1 out of 52 being the ace of hearts. We can illustrate these probabilities in some very simple ways. For instance, we can ask what is the highest hand that's possible in poker, right? So the answer to that question, if you don't know it, is the royal flush. It's basically the ace of hearts, the king of hearts, the queen of hearts, the jack of hearts, and the 10 of hearts, right? So what is the probability of dealing this hand in the order that's shown? So in other words, if I take my random deck of cards and I want to ask what is the probability that on the top of the deck I've got the ace, the king, the queen, the jack, and the 10, all of hearts, okay? The answer is you can calculate it, right? Because the probability of pulling the ace of hearts out is 1 out of 52. The probability of pulling the king of hearts out is now 1 out of 51 because the one card's already been pulled. The probability of pulling the queen of hearts out on the next draw is 1 out of 50 because 2 cards have been pulled out, right? So if you work out those numbers, it's about 1 in 311 million that you would deal that hand in order. So I've got my random deck of cards, and let's just see how lucky I am, right? So what are the chances that I pull the ace of hearts out? Well, that's going to be 1 out of 52, right? So there's the top card. Well, it's an ace of hearts. So I was pretty lucky. That was 1 out of 52 chances I would get that right. What's the probability that I'm going to get the king of hearts out on the next pull from the deck? Well, it's going to be 1 out of 51. So I take the top card. Well, I got a king of hearts. So that's pretty good, What about the Queen of Hearts? Oh, man, what a lucky guy. Jack of Hearts? Well, I got that one right too. And then the 10 of Hearts. Oh, there you go. So, I've done this experiment about 300 million times. This is the first time I've actually been able to generate this sequence of ace, king, queen, jack, and 10. So I'm a lucky guy today. And if you believe that, I got a bridge in Brooklyn I'd like to sell you. But that gives you the idea how to calculate these probabilities, right? And notice that we're multiplying the probabilities because these are all joint probabilities, right? So we have to multiply the probability of each event in order to get the total probability. I'll just comment by saying that if you want to calculate the probability of dealing a royal flush in any order in any of the 4 suits, right, I calculate that down here. It's about 1 in 650,000 to achieve that goal. And then the last example, I'm running a little late. The last example is basically placing 6 molecules, right, into 2 compartments of equal volume. So I've got compartment A and I've got compartment B, right? So let's say these 2 compartments are connected up together. I put 6 gas molecules in there, right? And I just want to know what's the probability that, let's say, all 6 gas molecules are in compartment B. What's the probability that, let's say, all 6 molecules are located in compartment A? So they can go back and forth, they can bounce around inside, right? And this problem is more of a physical problem, but it relies on all these probability discussions that we've had. And so you can map these discussions we've already gone through onto this problem, which is more of a physics or chemistry related problem. And you can identify the different states of the system, right? So the different states of the system are how many molecules are in compartment A versus how many molecules are in compartment B. You have to identify the weights of these different configurations, and these weights can be calculated using this very simple formulation of n choose n. So here we're choosing n particles to be in compartment A. We're choosing n sub B to be the number of particles in compartment B. The sum of n sub A and n sub B is 6. So that fixes 6 factorial in the numerator of this equation. And what you can do is you can generate these various weights. You can also generate the various probabilities. And you can prove to yourself that if you sum up all these probabilities, you do in fact get equal to unity. So to discuss this problem, right, we take over a lot of these ideas that we developed about pulling marbles out of hats or dealing cards out of a deck, right? They all can be translated and used to discuss some of these simple problems. So this is a very quick introduction to some of the concepts in statistical thermodynamics. We're going to come back in the next lecture and we're just going to discuss what happens when we start to let n, this n, the total number of particles that we're dealing with, what happens when that starts to get very, very large. And it turns out some interesting consequences occur, and I'd like to try to describe that to you in the next lecture. So come on back and listen to that. It's kind of a interesting development that probably don't anticipate just thinking about it on your own. So we'll see you then. Thank you.